Hi everyone, my name is Bhagwat Sai and today I am going to discuss about adjacency list and its storage and search efficiency. So let's move on with the topics.
In a graph, an adjacency list is a collection where each node has a list showing all the nodes it's directly connected to. Here is an example graph of adjacency list that consists of 5 nodes labeled as A, B, C, D, and E. Let's discuss about each node of the graph. Here, as we can see, node A is connected to B as well as C. Here, node B is connected to E as well as D. Here C is connected to node D. Here node D is connected to node A, node E and itself. Here let's see how adjacency graph is converted into adjacency list. In the adjacency graph, node A is connected to node B as well as node C. Whereas in the adjacency list, node A contains two blocks. One block contains node A and the other block contains address of the next node B. And B node contains two blocks. One block contains node B and the other block contain address of the next block C. And C contains two blocks. One block contains node C and the other block is null, which is empty because there is no node after node C. Here we can see how node B is connected to node D and E. Here we can see how node C is connected to node D. The second block of node D is empty because there is no node connected to it. Here we can see how node D is connected to node A, node E and itself. Here we can see node E is connected to no other nodes. The address space of node E is empty. Here let's see why adjacency list is efficient with storage and search. Coming to space efficiency, minimal storage. An adjacency list only stores the vertices and their direct connections, unlike an adjacency matrix, which stores all possible connections, even non existent ones. This means that for a graph with v vertices and e edges, the space complexity is order of v plus c. Sparse graph advantage. In graphs where most vertex pairs are not directly connected, an adjacency list saves significant space because it only records actual edges. Coming to reduced memory usage, linked structures. Adjacency lists use linked lists or dynamic arrays to store connections, which means they only allocate memory for existing edges. This reduces the amount of unused space in comparison to an adjacency matrix that allocates memory for every potential edge. Efficient iteration, traversing neighbors. When searching for the neighbors of a node, an adjacency list allows for direct and fast iteration. The neighbors can be listed in order of degree v time, which is much faster than scanning an entire row in an adjacency matrix order of v. Useful for algorithms. Algorithms like depth first search and breadth first search run efficiently using adjacency list as they can quickly access the neighbors of each node. Scalability scales with graph size. As the number of edges grow or shrinks, the adjacency list dynamically adjusts to use the necessary amount of memory. This adaptability ensures that resources are not wasted. Quick access to neighbors. Direct lookup. Each node in the adjacency list points directly to a list of its adjacent nodes. This setup allows algorithm to quickly access and iterate all over neighboring nodes without having to scan an entire data structure. Traversing adjacent nodes. Searching for adjacent nodes of a given vertex takes order of degree v time, which is efficient because it only processes the nodes that are directly connected. Optimized for traversal algorithms, DFS and BFS. Algorithms like depth first search and breadth first search are particularly efficient with adjacency list. where these algorithms need to explore a node's neighbors. They can quickly read through the adjacency list of that node, ensuring minimal time is spent on accessing the data. Time complexity. Traversal of an entire graph using DFS or BFS with an adjacency list has a time complexity of order of V plus E, where V is the number of vertices and E is the number of edges. This matches the total size of the adjacency list, ensuring that every node and edge is visited once. Dynamic edge lookup. Iterative search. If you need to find if a specific edge exists, it can be done by iterating over the adjacency list of node A. This operation has a time complexity of order of degree A, while not as fast as order of degree 1. In an adjacency matrix, it is generally efficient in sparse graphs where degrees are low. Efficient edge counting. Listing all edges. Listing all edges in a graph can be done directly by iterating through each node's adjacency list, which is faster than checking every possible edge in an adjacency matrix. This makes adjacency list ideal for operations where edge enumeration is necessary. Better space-time trade-off. Sparse graph efficiency. In sparse graphs, the adjacency list provides a better space-time trade-off. The list takes up space proportional to the number of edges and nodes, enabling faster lookups and lower memory use compared to an adjacency matrix. Conclusion. Adjacency lists are particularly efficient for storing and working with sparse graphs due to their reduced memory footprint and quick traversal capabilities. This efficiency makes them popular for many graph based algorithms and applications where space and traversal speed are critical. Thank you everyone. Please subscribe to my channel.